member of the Sheffield cohort, number 3. So what I'm looking at is high density heat storage for homes. I think Sol's probably knocking around the back of the room, who's my supervisor, Peter Starring, both at Sheffield. So ultimately, looking at this has basically indicated that phase change materials seem to be a good approach to this problem. They are pretty high energy dense, but really safety is one of the things that is quite important with homes and domestic sort of situations. And I wanted to look at using CFD to investigate what's going to go on in terms of convection, heat transfer, etc., if you were to integrate these into floors and walls. So the motivations for this are pretty simple. There's lots of you in this room that already know most of the motivations for energy storage in general, i.e. arbitrage. We're looking at diversified energy generation, which is going to be unstable, which presents a problem. So this is just there to help out. So if you imagine there being an entire neighbourhood that can control its heat storage, then you'll be able to schedule it in such a way that you can deal with problems. So computational fluid dynamics, what is it? Basically, it's a way of using a computer to model, in this case, melting and solidification cycles. And I've been using ANSYS Fluent to take care of this. And you can see up here is a two-dimensional domain. So I've been looking at modelling with this two-dimensional domain to make an infinite width. So the two walls there on the sides are mirrored. So if you imagine it being infinitely wide, which should be a good approximation for a floor, if you have it under the floor. Also we have. So jumping into some results, as you can see here, I've been comparing beeswax and paraffin wax. Beeswax has melted at around 8,000 seconds and paraffin wax at about 11,000. The interesting thing is that both of these are actually conduction dominant, as indicated by dimensionless number analysis, which is somewhat strange when you look at the velocity contours, and you can actually see that there's some convection going on in the paraffin wax. Now, unfortunately, the same dimensionless number analysis actually indicates that this convection is not what we want, because it's not in a turbulent regime, which is a sort of interesting result. So when doing models and when looking at the empirical testing later on to validate these, we do need some good data, because if you have garbage in, you get garbage out. So I've been doing some differential scanning calorimetry to characterize my materials, so getting the data for the models. Unfortunately, some of the materials that I've been testing do seem to exhibit some weirdness, which I think comes down to hysteresis. So the first cycle looks very different to some of the next cycles, so I'm going to have to look into this a bit more. As with all models, if you've got one in CFD, it's a good idea to validate it, and so I'm getting an experimental vessel put together, which you can see there, which has an array of temperature sensors, an infrared transmissive wall, so you can look at it with a thermal camera, and yet to be pictured the actual heating pads to go on the bottom. This bit is the electronics control side, so everyone that loves electronics probably has a Raspberry Pi, which you can see at the bottom there, which is basically doing the SCADA for me, which is supervisory control and data acquisition. So in terms of further work, I need to get some more DSC done to try and work out the source of the weirdness, finish the construction and do some more experiments on that rig that I'm getting built. Then write up the paper that I'm writing now on the comparison of those two PCMs, beeswax and paraffin wax, and then again another paper on actually validating my models. So, thank you for your attention. Has anyone got any questions?